Let's solve LeetCode 36 valid Sudoku. So we want to determine if a 9 by 9 Sudoku board is valid or not. Only the filled cells need to be validated according to the following rules. Each row must contain the digits 1 to 9 without repetition. Each column must contain the digits 1 to 9 without repetition. And each of the 9 3 by 3 subboxes of the grid must contain the digits 1 to 9 without repetition. What does that mean? Let's take a look at an example directly. So we are given an input of a list of strings. If the string is not a full stop, it's going to be filled. For example, 5 year is a filled cell, 3 year denotes a filled cell, 1 year denotes a filled cell. A full stop, however, denotes that a cell is empty. The same goes for all of these cells as well. So we want to ignore these cells. That's what's told to us, right? Because it says that only the filled cells need to be validated according to these rules. Now, what are our rules? Our rules are that each row, so everything that's horizontally laid out, each of these rows should be should contain the digits between 1 to 9 without repetition. So for example, we have 537. That's valid row. Remember that's just a valid row. It's not a valid grid. We have to check that if it's a valid row for each of the rows that are present. 863, 4831, 726, etc. Let's take a look at an invalid board. So here there is an invalid board given to us. There's no diagram, unfortunately, but we can try to figure it out on our own. So 837 is a valid row, 6195 is also valid, 986 is also valid, 863 is also valid, 4831 is also valid, 726 as well, 628, 4195, 879. Everything's valid here, right? Each of the rows is valid. Why is it not a valid Sudoku then? That's because there are two more conditions to be fulfilled, and that is each column must contain the digits 1 to 9 without repetition. So let's check for that. So we have 86847, and there we see the problem. We have two duplicate digits here, 8 and 8 in the same column. So if you look at the explanation, it will tell the same thing, but not the exact same thing. It will tell you another reason of why it's invalid, which is since there are two 8s in the top left 3 by 3 sub box. To understand this explanation, we need to understand the third rule, which is each of the 9 3 by 3 sub boxes of the grid must contain the digits 1 to 9 without repetition. What does that mean? Well, remember, this is a 9 by 9 Sudoku board, right? So we have 9 rows and we have 9 columns. So the 3 by 3 sub box that they're talking about is this particular box, or this particular box, or this particular box. So these are all 3 by 3 sub boxes, and there are 9 in total, right? Because this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 of these boxes. And each of these boxes should also contain the digits 1 to 9 without repetition. Only then is the Sudoku board valid. Now, the very first thing that will come to your mind is, hey, how do I figure out if it's valid or not? Because the cells here are empty. If the cells are empty, anything can go into it. A 9 can also go here and it would make the board invalid, and that's true. But if you look at the question again, it's going to say that only the filled cells need to be validated according to the rules. And in the note, it's saying that a Sudoku board, even if it's partially filled, could be valid, but it's not necessarily solvable. So solvable and valid are not the same things. If it's solvable, it's solvable. If it's valid, then it's valid. One does not imply the other. So if it's valid, does not imply that it's solvable. But obviously, if it's solvable, it is going to be valid, because it was solvable because it was valid, but not the other way around. Anyways, not to confuse you any further, let's take a look at the last note, which is only the filled cells need to be validated according to the mentioned rules, and I've talked about that. So if it's basically a full stop that's given to us, a full stop in our list of strings denotes an empty cell, right? So if you look here, an empty cell is dot. So we'll ignore that. Now, how do I figure out if a particular row, a particular column, and a particular sub box is having the digits 1 to 9 or not? Let's start one by one. So the very first thing we want to do is check out the rows. So I need to figure out if all of these rows are valid. Now, to ensure they're valid or not, what can I do? Well, first of all, how can I iterate through all of the elements that are present in the list of strings? Obviously, we'll have to use a double for loop, correct? So what we'll have to do is for I in range, and we'll have to go through the entire list, right? So how many ever list items are present here for each of the array that's present in the list? So let's say this was a list of string. So we are going over each list in this mega list. Okay. So we go over each of the list that is present here. So for I in range, the length of this particular grid. And if we go over each array that's present here, what are we doing? If we go over each one of them, we are going over each row, right? Because if we go over this particular thing, we are going over 537, which is the first row, 6195, which is the second row, and so on. So I denotes the row. Then what we want to do is go over every element that's present within the array, right? So let's say we are on this array. We need to go over every element in this array. So we have 5, 3, 7. So we go over it individually. The same goes for 6, 1, 9, etc. So now what I'll do is for j in range of this length of grid of I. Doing that will give me the column count. Why? That's because if I am at I is equal to 0 and j is equal to 0, it would mean I'm over here. If I is equal to 0, I'm on this particular thing, and j equals 1 means I'm over here, right? Because on the 0th array, I'm on the first index. Cool? If I'm on I is equal to 0, j is equal to 2, I'm over here. Now that's the Python basics, but I wanted to give you an intuition of what these two represent really. This represents row and this represents column. So now that we have this in place, we know how to iterate over each element, and now we know what the unique identifier for each row is. Each row is identified by 0, 1, 2, 3, 4, 5, 6, 7, 8. So we can denote all of the rows by I, and we can denote all of the columns by j, and that is their unique identifier. Why am I stressing so much on unique identifiers? That's because we are going to use them. Now, let's come back to our objective. Our objective is to find out if there are any duplicate elements over here. Now, how can I find that out? What I can do is store them in a list, right? So I'll go over each element here and store it in a list, 5, 3, 7. Cool. And before adding each element to the list, I'll just check, hey, does 5 exist in this list? Does 3 exist in this list? Does 7 already exist in this list? If it does exist, that means it's not a valid Sudoku. We'll instantly return false. If it does not exist, that means we're good. So this is how we figure it out. But we have to do it for each of the rows, right? So having understood that, we know how we are going to store this in a list. But how are we going to keep track of all of the rows that are present here? And to keep track of all of the rows, what we're going to do is create a mapping. The mapping is going to be between 0th index and then the list. Also, one small thing, we already know that if we want to check within a particular data structure and we want to ensure that its time complexity does not increase, we'll just use a set instead, right? Because set is O of 1. So instead of using a list, we can use set, and it won't really make much of a difference, but we get the nice O of 1 time complexity, and that's good. So we'll do 0 with an empty set, 1 with an empty set, 2 with an empty set, and so on. And when we go over each element, we can append it or add it to the set. So we'll have 537, 6195, etc. So that is the first thing. How are we going to do it for columns? Columns is going to be the exact same thing. Columns is also going to contain a dictionary which contains the mapping, and the mapping is going to be like this: 0, 1, 2, 3, 4, 5, 6, 7, 8. Cool. And then I can just store it. So at 0, the columns that we have, the elements that we have is 5, 6, 8, 4, 7. Cool. Then at index 1, we'll have 3, 9, and 6. As soon as we see a duplicate element in the row or the column, we can just return. Now, how about the subgrid? These two were quite easy. Subgrid, how are we going to do that? That's going to be a challenge, right? No, we're going to use the same concept. But instead of using this thing, instead of just 0, 1, and 2, just one number, we're going to use two numbers as the unique identifier or as the key of the dictionary for the 3x3 grid. Why are we doing that? That's because each subgrid is not, one-dimensional thing. For row, everything was one-dimensional. So everything is just in one-dimensional. So we can just denote it by one number. But when we are in a grid, a 3x3 grid, we are in two-dimensional space. If we are in two-dimensional space, we need two numbers to represent the spot. Because if you say, let's say you create a dictionary which contains the mapping like this: 0 is 5 and 3. That's not correct, because what you're doing is creating a row. 5, 3 will create a row. We can't do that. What we need to do instead is that at 0 position, and let's say 0 position, we are going to have 5, 3, 6, 9, 8. Why am I saying that? That's because what we are going to do is divide it by 3. So I will be divided by 3, j will be divided by 3, and they will be stored as the key in a tuple, and then we'll get our answers. So what that means is that this first thing is going to be denoted by 0, 0. The second thing is going to be denoted by 0, 1. The third thing will be denoted by 0, 2. Then this will be denoted by, guess what? 1, 0. This will be 1, 1, 1, 2. Then we'll finally have 2, 0, 2, 1, and 2, 2. So this is how a mapping is going to be stored. We need two numbers for this particular reason. It's two-dimensional. And we want to store all of these numbers together. How are we going to store all of these numbers together? We can just divide the I by 3, divide the j by 3, and we'll get the representation, correct? So that's what we are going to do. Let's quickly code it out. And if you want, I can again explain it to you. But we'll start off by creating a dictionary, 3 dictionaries, by the way. So there's going to be a column dictionary, which is going to be this. Then we are going to have a row dictionary. And do you think just doing this much is enough? Well, we can create it like this, but what I like to do is again use default dictionary, where the value is initialized to an empty set. As I mentioned, we are going to store everything in a set so that the time complexity to just look up an element can be O of 1. Even then, even if you don't store it, it shouldn't be a problem, because at max, we can only have 9 elements stored in the list. So even if you use a list, it's fine. It's just going to be O of 9, because in the worst case scenario, we're only going to have 9 elements. But either ways, let's optimize this process. We'll just have a default dict of set for each one, and then I'll have a 3x3 dict. This will contain the 3x3 grids, and there we go. After that, I'll go over all of the elements in the board, correct? And this gives me the row. Now I'll go over every column essentially. So I'll have length of board at I. So I'll go over every element in this array, and when I go sequentially here, I get access to 0, 1, 2, and that gives me the column index, sorry. So now that I have column index with me, what I can do is first of all, just check if the element is a full stop, because if it's a full stop, we want to ignore it because we want to, just ignore the empty cells. Because let's say we add the empty cell to our row dictionary or column dictionary. In that case, we'll run into errors quickly, because in the first row itself, it will think it's invalid Sudoku because there are 2 empty cells and cells are full stops. So both of the cells are going to match with each other, and we do not want that. So what we can do is, in the very first thing, we'll have if board at I at j is equal to a full stop. In that case, we are going to continue. After that, what we're going to do, if the board at I at j is a valid string. By the way, it's a very important assumption that we're putting in, that the digits here are going to be string all the time. So string of numbers, it can't be anything else. That's what we are assuming. And we can assume that because it's given here, but it's good to ask with your interviewer. So let's go ahead and update the row dictionary. So row dictionary at I, remember row dictionary at I, because we want to update the 0th index in the dictionary and add elements to it. So row dictionary at I is equal to, or I don't want to do is equal to, I'll just add the element at board at I at j. Cool. Now, doing this, writing this line of code might have made you understand why we are creating a mapping. Okay. We're creating the mapping once again because we want to store each of these rows. Okay. And the reason we want to store each of these rows is because, we want to know if each of the row is valid or not. So when we go sequentially over it, we can just access the element like this. So if the board at I, so let's say board at 0 contains the value that's present within the set or not. So that's what we're doing. Now we'll do the same thing, but for column dictionary. So we'll have column dictionary at j.add, and then we'll add the element, which is board at I at j. And then we need to do it for a 3x3 dictionary, which is going to be 3x3 dictionary. And then I told you that this is going to be a 2-dimensional space. It's going to be represented by 2 numbers. And the 2 numbers are a tuple. And the tuple is going to be something like this. So the very first thing is going to be I divided by 3 and j divided by 3. Again, the reason we are dividing by 3 is because we have the indices 0, 1, and 2. Coming back here, let me just remove everything. I'll copy this so that we have a fresh perspective now. And let's draw it out. So the reason it's going to be 3 is because this is index 0, 1, 2, and this one is 3. This is where the separation occurs. So if we do 0 divided by 3, it's going to give us 0. 1 divided by 3 is going to give us 0. Now the reason 1 divided by 3 gives us 0 and not 0.33 is because I've used this. 1 divided by 3 like this will give us 0.33, but 1 double divided by 3 is a floor division. So what it does is takes your value and pulls it down to a whole number, So it's going to be 0 now. Then we are going to have 2 divided by 3, which is also going to be 0. And then when we go to 3 divided by 3, we're going to have 1. And 1 means it's a different cell altogether. That's what allows us to create the separation. And now, since we have that key here in place, we've created a tuple because we've seen in previous problems that if you want to specify the key of a dictionary, you have to make it a tuple. And then I'll just add, and what I want to add is board at I at j. Now just doing this much is not enough because there's more to do. As of now, we've just added the elements, but who's going to put the check that, hey, the board at ij is present in column dictionary already, or is it present in row dictionary already, or is it present in 3x3 dictionary already? So we'll just put a check here, and we'll do it before we add. All right. So before we add, we're going to check, hey, if the element which is board at I at j, if it's already present in the row dictionary, which is at I, or the board at I at j in column dictionary at j, or board at I at j in the 3x3 dictionary. So let's take this 3x3 dictionary at, and then we again need to create a tuple that we created here, I divided by 3, j divided by 3. And then if this is the case, we'll just return false, because the element is already present in the specified row or the specified column or the specified 3x3 grid. But if it's not present and the entire loops get over, everything gets over, we still don't return, then we are going to return true, that hey, it's a valid Sudoku, everything passed. So let's run and hope it gets succeeded. And it does succeed. Let's submit it. And it works out. So just to explain the entire code to you again, what we're doing is creating the column, row, and 3x3 dictionary. We are looping through every element that we get, and we're storing them in their respective row dictionary, column dictionary, and 3x3 dictionary. For row dictionary, we are using I because we are going over every array or every list which specifies which corresponds to a row. Then we're going over every element which gives us the chance to index the column. And then we have a 3x3 dictionary which is corresponding to the indices of I and the indices of j. So that's how everything works out. And yeah, so that's the entire thing. Now, what is the time complexity of this entire solution? The time complexity of this is O of n? No, it's not O of n. It's not O of n into m either. What it is actually is O of 81. What did I just say? Yes. The time complexity here is O of 81. The reason for that is because it's always going to be a 9x9 Sudoku board. So when we do for I in range length of board, what we are doing is going over every element in this board. So we go over every array, and there are 9 arrays. And then we go over every element, or let's say every column, and we have 9 columns. So 9 into 9, 81. For every single problem, we're going to go over 81 iterations. It's not going to exceed. It's not going to be minimum. At least, I hope not. Or actually, it might be, because, this condition can be reached. So we can return false. If we return false, we're never going to reach 81 iterations. But yeah, it cannot exceed 81 iterations is the main thing. And it's not really dependent on the input, right? Because even if I change this and put range of 9, for example, it's going to work out. And even here, if I remove everything and put in 9, it's going to work out. That's because we know it's a 9x9 Sudoku board. That makes our time complexity O of 81 because we are only having 81 iterations. And we know that if it's a constant, the time complexity is O of 1. And the space complexity is also O of 81. That's because we can store 81 elements in these two dictionaries. And then there's a third dictionary where we can store more. But essentially, the thing is, it's going to be O of 1 as well, because it's going to be a constant value. So that is the time and space complexity. It's quite interesting that it's not O of n into m. And even if you do say it's O of n into m, you can specify that n is the length of the board, so the number of arrays in the board, and then the m is the number of columns that are present within the board, and still you'll get O of 81 because all we're doing is rows into columns. So yeah, that's the solution.